In this revision video, we are going to answer some selected organic reaction questions. In these selected organic reaction questions, we are going to answer them, and for the purpose of revision, we may have to revisit what we discussed in our previous video. Before continuing with our revision today, please like this video and subscribe to our channel. Do not forget to hit the notification bell. Welcome back. We will be starting with question number 1. A reaction sequence is shown. Bromoethane undergoes reaction 1 to form propanenitrile. Propanenitrile undergoes reaction 2 to produce propanoic acid. Propanoic acid undergoes reaction 3 using LiAlH4, that is lithium tetrahydroaluminate, to produce W. Now, again, bromoethane undergoes reaction 4 to produce ethanol. Again, bromoethane undergoes reaction 5 to produce ethene. A. Complete the diagram to show the mechanism of reaction 1. Include all necessary charges, partial charges, lone pairs, and curly arrows. Yes, you have seen it. This is the question. The first thing that comes to your mind, this is a halogenoalkane. What type of reaction is this? Okay, this is a halogenoalkane. This bromoethane is a halogenoalkane. Now, the second thing that comes to your brain is what type of reaction do halogenoalkanes undergo? In terms of the mechanism, we have 3 types of halogenoalkanes. Remember, we have 3 types of halogenoalkanes. There is primary, there is secondary, and there is tertiary tertiary halogenoalkane. In this case, for the purpose of a revision, what type of reaction or reaction mechanism does primary halogenoalkane undergo? You are supposed to know the type of reaction mechanism that primary halogenoalkane undergo, secondary halogenoalkane undergo, and tertiary halogenoalkane undergo. But in this situation, we have a primary halogenoalkane. What type of reaction mechanism does it undergo? The next thing that should come to your brain is it an SN1 or is it an SN2? It is an SN2. This is an SN2 mechanism. Then in SN2 mechanism, what happened in SN2 mechanism? What should come to your brain is that in SN2 mechanism, the word implies, SN2. SN2 is, we are talking of nucleophilic substitution bimolecular. It means that there are two reacting species involved in the rate determining step. Here there is bromine and there is the cyanide ion that are really involved in this in this reaction. It is an SN2 mechanism because there are two reacting species. In this mechanism, for the purpose of revision, what happened? You should remember that this is a one-step reaction because there is bond formation with the nucleophile, which is the cyanide. There is bond formation with the nucleophile, which is the cyanide. And there is heterolytic bond breaking with the halogen, which is the bromine, taking place at the same time. You should also remember that there is no carbocation in this reaction in an SN2 mechanism. So, for the purpose of revision, let me just brief you. Remember that the nucleophile approaches what? The molecule. The nucleophile approaches the primary halogenoalkane. This is a primary halogenoalkane. The nucleophile approaches this bromoethane from the opposite side of bromine. It should also be remembered that this is the carbon-bromine bond is polar because of the difference in electronegativity. Carbon is will now take a partial positive charge and bromine a partial negative charge. The nucleophile approaches the bromoethane from the opposite side of the bromine because one, the partial negative bromine will hinder the nucleophile, or it will repel the nucleophile from approaching it from this side, from the side of the bromine. It will hinder this from approaching it from this side. So it will only have to attack but from behind. Another reason, in primary halogenoalkane, the opposite side of the bromine is not clustered. It's not choked up by alkyl groups. There's only one alkyl group there. It's not choked up by alkyl groups. There's space here for the nucleophile, which is the cyanide, to attack but from behind. The third reason is because it is the inductive effect. There's only one alkyl group here, please. For that reason, the inductive effect of this alkyl group on the carbon having the bromine, on this central carbon atom having the bromine, the inductive effect here, excuse me, makes this molecule, it makes the molecule to be relatively unstable and result in a very high activation energy of the reaction. And when that happens, when the nucleophile approaches, when the nucleophile now approach the partial positive carbon, what happened? It donates a lone pair of electron. When it is donating a lone pair of electron, the carbon bromine bond, the electrons in the carbon bromine bond are shifted towards the bromine. And what happens? Eventually, a transition state where the carbon bromine bond is just at the point of breaking, and the carbon nucleophile bond is just at the point of forming will occur. That will be a transition state. In this transition state, there are usually 5 groups attached to the central carbon. That is the central. That is the central carbon, which is the partial positive carbon. This mechanism will go on until the nucleophile is firmly attached, and the bromine finally breaks heterolytically and expelled as what? As a bromide ion. And the bromide ion now goes with a lone pair of electrons. At this point, the nucleophile has substituted the bromine. Let me just show you what I am trying to explain here for the purpose of revision. Here, what happens here? As the nucleophile is approaching the partial positive carbon, what happened? What is happening there? Electrons here are repelled towards the bromine. The bonding electrons here are repelled towards the bromine. The bromine is shifting and going further and further. Now, as the carbon, the nucleophile carbon bond is about forming, this is it here. The carbon-bromine bond is about breaking. We call this a transition state or an intermediate state. We call it a transition state or an intermediate state, where the carbon nucleophile bond is forming, while the carbon-bromine bond is about breaking. There is a transition state there. And I said there are 5 different bonds involved here. We have 1, 2, 3, 4, 5 at the transition state. There is bond formation and bond breaking at this stage. And eventually, I said, it gets to a point where the carbon nucleophile bond, the nucleophile firmly attached itself to the central carbon. And the bromine finally breaks off as a bromide ion with a lone pair of electrons. And this is how that is formed. Now we see a propane nitride is formed, and a bromide ion with a lone pair of electrons is also formed. So now, that is the purpose, that is only for revision purpose. If you were in an examination room, dear learners, if you were in an examination room and you were to answer this question, this is how you are going to place your answers. I said, for the purpose, if you are in an examination room, this is what is expected of you. Now, the bond is partially, because of the different electronegativity, this is partial positive, and this is partial negative. That is what you are supposed to do. Now, you have to indicate here the lone pairs of electrons that are here. They are here from the cyanide. The cyanide has a lone pair of electrons. Being a nucleophile, nucleophiles are electron pair donor. So as they are approaching the partial positive carbon here, they are donating that lone pair of electron here. And what happens? The bond between carbon and bromine, as these electrons are approaching here, there is repulsion. The bonds are being shifted, the electrons are being shifted towards bromine. So we indicate that using our curly arrows. We will have this here. That is how it goes. It is supposed to be. Then using, as it is approaching the partial positive carbon, what happens? Electrons are repelled towards the partial negative bromine. That is what is supposed to happen. Now, it comes to a transition state. There is supposed to be a transition state, but they did not ask us to show the transition state. What I showed you here was for the purpose of revision. So we have shown our curly arrow because they have said curly arrows. There's one curly arrow from shifting of electrons to bromine, and there's another one from the nucleophile to attacking the partial positive. Those are the two curly arrows that are involved in this thing. Then what is the product as I showed you there? When this one from the transition state, when bromine finally breaks off heterolytically with a lone pair of electrons, this other one, the cyanide, firmly attaches itself to the central carbon. And this is what happens here. And the bromine is now left here as the bromide ion. That will be the bromide ion with a lone pair of electrons, indicating a bromide ion. That is how the whole thing is supposed to be. You can show your bromine with a lone pair of electron and showing that it's an ion. You can show the charges, the charges between the bromine, carbon and bromine bond. Then you can movement of a lone pair of electron from the cyanide to the central partial positive carbon, and then I think everything will be okay. We have altogether 2 marks for that. B1. So that is it. One more for the purpose of revision. The examiner is very tricky. At times, they can put everything on, they can put the arrow, the curly arrows, and then they put the product and ask you to draw the transition state. This is how the transition or the intermediate is supposed to look like. So you should be versed with everything. What is happening in the transition state, what is happening, the product, the transition state, and what is happening with the reactant with the reacting species. Okay, it takes us to the B part of it. Give the name of the type of reaction involved in reaction 3. B1, reaction 3. This is propane nitride. Propane nitride is our product here, that is from here. Reaction 3 has to do with reaction 3 has to do with reduction. It has to do with reduction. Lithium tetrahydroaluminate or sodium tetrahydroborate. These are reducing agents. They use this for reduction reaction. And in a reduction reaction, aldehyde in a reduction reaction, primary alcohols are reduced to aldehydes, and are now finally primary alcohols are reduced to aldehydes. So in this case, you will see that aldehydes reduction reaction is the reverse of oxidation reaction. Reaction is the reverse of oxidation reaction. For instance, let me say for this, let me use this. If we have, for the purpose of revision, we will have primary alcohols. We will have primary alcohols. The primary alcohols are reduced or are oxidized are oxidized to aldehyde. They are now primary alcohol are oxidized to aldehydes. They are oxidized to aldehydes. And they are further again, primary alcohol are oxidized to aldehydes and are further oxidized to what? Carboxylic acid, corresponding carboxylic acid. There is a reverse. The same way we reduce this. In oxidation, we will use either potassium dichromate, acidified potassium dichromate 6, or we will use acidified manganate 7. That is for oxidation. For reduction, we will either use lithium tetrahydroaluminate, or we will use lithium tetrahydroaluminate in dry ether, or we will use sodium tetrahydroborate. We will use lithium tetrahydroaluminate in dry ether, or we will use sodium tetrahydroborate in aqueous alcoholic solution. So we can use this reagent and reduce carboxylic acid to what? To aldehyde again. Reduce them to aldehyde again, which is further again reduced to primary alcohol. So I am indirectly telling you that reduction is the reverse of oxidation. If you can oxidize primary alcohol to corresponding carboxylic acid using suitable oxidizing agent like potassium acidified potassium dichromate 6 or acidified potassium manganate 7, we can oxidize that using that. Conversely, or alternatively, we can reduce the carboxylic acid back to the primary alcohol using lithium tetrahydroaluminate or sodium tetrahydroborate. So this reagent that you saw in the question is used for reduction, and this acid can be reduced to the corresponding primary alcohol. Let's go back to the question. Therefore, in this question here, carboxylic acid is being reduced to a certain compound W we don't know. From our discussion, if it is propanoic acid, it will be reduced to its primary corresponding primary alcohol, and which will be what? It will be propan-1-ol. If it was ethanoic acid, for reduction, we will have ethanol. If it was butanoic acid, we will have butan-1-ol. So this is a primary alcohol. This is an acid that have been reduced to what? That have been reduced using this reducing agent to its primary alcohol. And the primary alcohol for propanoic acid is propan-1-ol. So give the name of the type of reaction involved in this reaction. Reaction 3 is reduction. We will call it a reduction reaction. That is a reduction reaction because we are reducing the acid to its corresponding primary alcohol, which is propan-1-ol. Okay, it takes us to The other part of B, this question involves the infrared spectroscopy. The infrared spectrum of propanoic acid. The infrared spectrum of the propanoic acid produced by the reaction 2 is shown. This is shown. That's reaction 2. That is reaction 2. Okay. From propane nitride to propanoic acid. This is the infrared spectrum of propanoic acid produced by the reaction 2. This is the reaction from 500, the wave number from 500 to 4,000. The transmitter is there. You have seen it well. Look at the peaks very well. Where there is where the peaks are broad, where they are sharp. Now, the question is, describe and explain the main difference between the infrared spectrum of the compound that was produced here, W, and that of propanoic acid. Very good. This reduction process, the first thing is, if you can't get the product W, the identity of W, you will not know how to give the difference, the differences. So now, I said this is reduced to a corresponding primary alcohol. Is the reverse of oxidation. And the corresponding primary alcohol for propanoic acid is propan-1-ol. For propan-1-ol, let's see what we can differentiate before we come there. You know the compound first, and we can now differentiate it. Propan-1-ol. This is propan-1-ol. Propan-1-ol is a CH3, CH2, CH2OH. Now, propanoic acid is CH2, CH3, CH2. Okay, these two. From these two from these two compounds or molecules, both of them have the CH bond. Both of them have the CH bond. Propanoic acid, if you look at it critically, propanoic acid, the acid and the alcohol. What is the difference? The acid will have the carbonyl group. It is absent in alcohol. The carbonyl functional group is present in carboxylic acid, in propanoic acid, but it is not there in propan-1-ol. In the acid, we have the OH bond. In the alcohol, in propan-1-ol, there is the formation of the OH bond now. But the absorption range of the OH bond in acid is different from the one of the alcohol. Then, of course, both of them, they have the CH bond, So all of them have the CH bond. So in that case, all of them have the CH bond. All of them have this. The only difference comes here. The only difference comes here and here. The functional group, the carbonyl functional group, is present in a propanoic acid, but is absent in propan-1-ol. The OH is also present in acid, and the OH bond is also present in alcohol, but the absorption range is different. So now we now go back. We can now see look at our. We now go to our data booklet. When you see such a question, open to your data booklet. When you now identify the differences, open to your data booklet. In your data booklet, the OH bond for the carboxylic acid, the OH bond for the carboxylic acid is 2000. The OH bond in the carboxylic acid is 2,500 to 3,000. That is 2,500 to 3,000. Then the OH bond in the alcohol here is from 3,200 to 3,600. Then go to the carbonyl group, which is present only in the acid. The carbonyl group here, ketones and aldehyde, yeah, it will definitely be from 1670 to 1740. So now, the infrared spectrum for the alcohol, what you should notice that the infrared spectrum for the alcohol will not contain the peak. The infrared spectrum for propan-1-ol will have no peak. There will be no peak within the range of 1670 to 1740 because there is no carbonyl group in the alcohol. But in the acid, in propanoic acid, we will have this peak. The peak is present in propanoic acid, but in propan-1-ol, the peak will be absent. Due to what? The peak will be absent because propan-1-ol do not have the carbonyl group. Another difference is that the peak in the alcohol or in propan-1-ol, there will be a peak. There will be a peak at within the absorption range of 3,200 to 3,600. In the compound W, which is propan-1-ol, there will be a peak at 3,200 to 3,600. Because of what? Because of the formation of the OH group. So let's go to our question paper. So when you have such a question on infrared spectrum, learners, open to your data booklet, get the differences, go to the data booklet, get the relevant data there, and use the relevant data there to answer your question. For instance, in this case, using my book of data, I can now say here, excuse me, I can now say, I can write there that W I can say W is equal to propan-1-ol. Propan-1-ol. W is propan-1-ol and has no carbon oxygen bond. W is propan-1-ol, or W equals to propan-1-ol. This has no C double bond O bond. But propanoic acid has it. But propanoic acid has it. Then I can say the I arrow of W. The I arrow of W has no peaks. It has no peaks It has no peak within. It has no peak within 1670 to 1740 absorption range. It has no peak. It has no peak within 1670 to 1740 absorption range. Because that's the reason. Because of the absence of. Because of the absence of the C bond in it. That is just that. I said W, the compound W is propan-1-ol. And the propan-1-ol has no carbon double bond oxygen. Carbon double bond oxygen. But propanoic acid has it. That is the difference. Secondly, the infrared spectrum of the compound W will have no peak within 1670 to 1740 absorption range because of the absence of the C double bond O in it, or the C double O, the C double bond in it, C double bond O in it. Another reason could be that if you don't give the reason, you can give the second reason is that, as I told you, let's go back to our data booklet. If you don't give the one regarding the carbonyl group, you can use the OH. You can say in compound W, which is propan-1-ol, there will be a peak. There will be a peak between 3,200 to 3,600 absorption range. Because of what? Because in propan-1-ol, there is the formation of the OH bond. But in propanoic acid, the peak is at 2,500. And is the peak, the OH bond peak in propanoic acid is between 2,500 and 3,000. But the OH bond peak in the alcohol, in the propan-1-ol, which is the compound W, will be between 3,200 and 3,600. So there are two differences you can give. You can give the one for the carbonyl group, or you can give the one for the OH group. Thank you. Let's go to the second, to the next part of it. For more videos or for more information on the infrared spectrum or spectroscopy, I referred to our previous video on it. Okay, let's go to the next question, which is C1. Reaction 4 and reaction 5 use the same reagent. 4 and 5 use the same reagent. Give the reagent and condition needed for 4. Reaction 4 and 5. Reaction 4 and 5. Reaction 4 and 5. Bromoethane undergoes reaction 4 to form ethanol. And bromoethane also undergo reaction 5 to form ethene. For the purpose of revision once more, when we were in our previous video on halogenoalkanes, and when we were treating the SN2 reaction mechanism, we used bromoethane and aqueous sodium hydroxide in the formation of ethanol. And in that video, I did mention that when bromoethane is heated under reflux with aqueous sodium hydroxide, In a solvent of aqueous ethanol, the bromine is substituted by the OH group and the ethanol is formed. I said in the previous video, you can go back there and watch it. When bromoethane is heated under reflux with aqueous ethanol, with aqueous sodium hydroxide in a solvent of aqueous ethanol, the bromine is substituted by the OH group and the ethanol is formed. So you now see that sodium hydroxide is used here everywhere. So now in our reaction, back to the question, give the reagent and condition needed for reaction 4. In the formation of reaction 4 for ethanol, as I've just said, the reagent there will definitely be sodium hydroxide. And the condition is this. Is it in aqueous condition? Is it concentrated? So what did I mention? I said when bromoethane is heated under reflux with aqueous sodium hydroxide. So the condition is what? It is aqueous. That's aqueous condition. Then give the condition needed for reaction 5. Reaction 5. Reaction 5. Reaction 5 is bromoethane to form ethene. Remember that when bromoethane is reacted with alcoholic sodium hydroxide, we are talking of ethanol. Alcoholic, when bromoethane is reacted with alcoholic sodium hydroxide, an ethene molecule is produced. And in this case, the alcoholic sodium hydroxide, we are talking of what? The condition is what? They say give the condition needed for 5 is alcoholic, which is what? Ethanol. Alcoholic sodium hydroxide. So the condition is what? Is under alcoholic condition. And which is what? Ethanol. So it now drives us to the D part of it. The D part of it, under appropriate conditions, ethanol and propanoic acid undergo a condensation reaction. State the condition necessary for the reaction. What is a condensation? Reaction? A condensation reaction, that is, there is an elimination of water, removal of water. So now, state the condition necessary for the reaction. When ethanol and the propanoic acid will react, a molecule of water is removed. In that case, that is esterification. In that case, an ether is being produced when a molecule of water is being released. So for esterification, there are some conditions that are necessary for esterification to take place. In esterification, in our previous video on esters, you will see that in our previous video on esters, you will definitely see this. You will find this. You will see that when propanoic acid react with ethanol, When propanoic acid reacts with ethanol, there is a condensation reaction. A molecule of water is being removed from this reaction here. And an ester is being formed. The condition here is propanoic acid and ethanol, when mixed together and heated under reflux. With what? With concentrated sulfuric acid. The concentrated sulfuric acid is acting as a catalyst. Either you use concentrated sulfuric acid, or you can still use concentrated, phosphoric acid. You could use concentrated phosphoric acid. You can either use this, or you use concentrated sulfuric acid. These are the two acids that you can use. And the reaction mixture is heated under reflux. What will be the product? The product will be an ester that is being formed with the elimination of a molecule of water. And this is what happens. For the purpose of revision, this is what will happen during the reaction. Our condition here will be what? Concentrated sulfuric acid acting as catalyst, or concentrated phosphoric acid and heated under reflux. So we will have an ester. And in naming ester, how do you do? The first esters have two names. The names of esters are in two parts. The first part of the name comes from the alcohol. The ethyl group, the alkyl group from the alcohol will provide the first part of the name. Then the second part of the name is provided by the acid. So in this reaction, the first part of the name is from the alkyl group produced by the alcohol, and the alkyl group produced by the alcohol is what? Is an ethyl group. The second part comes from the acid, which is propanoate. And now the name of the ester will be what? We start with the first part of the name, which is from the alcohol, and end with that part which comes from the acid. We will now say it is ethyl propanoate. Ethyl propanoate. Let's go back to our question paper. In our question paper, under appropriate condition, ethanol and propanoic acid undergo a condensation reaction. State the condition necessary for the reaction. From what we have just discussed, the condition will have concentrated, or will be concentrated sulfuric acid, which is acting as catalyst, or concentrated as phosphoric acid, concentrated phosphoric acid. You can also heat under reflux. Concentrated sulfuric acid or concentrated phosphoric acid, and we heat it under reflux. Now they say, okay, from our structure here, the second part of it is draw the skeletal formula of the organic product of this reaction. Let's go back to our reaction here. This is our reaction product that we have got. Excuse me. This is our reaction product that we have got. Here we have, this is the structural formula of the product. The formula you see here is the structural formula. This is the structural formula, but we have been asked to draw the skeletal formula. In drawing the skeletal formula for this, we have 3 carbons here. We have 3 carbons here. The first carbon, the second carbon, and the third carbon. This is how we draw the skeletal formula. We start from a point like this. Our starting point is a carbon atom. That is a methyl group there. From the first carbon, we go to the second carbon. This is the first carbon. This is the second carbon. The second carbon, we go now to the third carbon. It is in a zigzag form. The skeletal formula in a zigzag form. The first carbon is here. The second carbon is here. The third carbon is here. Remember on the third carbon, there is a double bond oxygen. In that case, we need to put the double bond here. Oxygen. Then again, we are continuing from here. This is the first carbon, this is the second carbon, and this is the third carbon. We are continuing from the third carbon. On the third carbon, remember the third carbon is bonded to oxygen. We now say, I said it is in a zigzag form. It now bonded to oxygen. This is now the oxygen here. From the oxygen, is now bonded to this other carbon. So we now come again, this other carbon. Now, then we now go to the last carbon. That is how a structure, a skeletal formula is drawn. Remember, we start here, we ascend, we drop, we ascend, we drop, we ascend. That is how a skeletal formula is being drawn. So let's go back to our question paper and see how we can represent it there. In our question paper, as I said, this is the first carbon. It goes here. This is the second carbon. The second carbon now goes to the third carbon. This is the second carbon. We now go to this. Now this is the first carbon. This is the second carbon. This is the third carbon. The third carbon is bonded to what? From our structure, the third carbon is bonded to oxygen. There's a double bond there. Now, remember, the third carbon is also bonded to oxygen. Now the oxygen again is bonded to another carbon. And the last carbon, that is how you draw the structural form, the skeletal formula in a zigzag form. We start from the first carbon. Each first carbon is a methyl group. So the first carbon, it ascends. When you get to the second carbon, you descend like that, and attaching all the side chains that are there. So this is the skeletal formula for the product that we had. Our product was ethyl propanoate. So now, okay, the name of the product, okay, I said the product is ethyl propanoate. Okay, it takes us to, and that was just one mark, it takes us to the E part. The E part of this reaction has to do with a reaction of alkenes. V reacts with acidified manganate 7 ion in 2 different ways, depending on the conditions, as shown in the reaction sequence below. Okay, you will see that this is V. This is V. V undergoes reacts with hot concentrated manganate 7, hot concentrated acidified manganate 7. Okay, and they said this is propanoic acid that is formed. V reacts again with cold dilute manganate acidified manganate 7. It forms T. We are told V decolorizes bromine water. Alkanes do not decolorize bromine water. Halogenoalkanes do not decolorize bromine water. Esters do not do that. The well-recognized organic compound that will do that are alkenes. Only alkenes will decolorize bromine water. Now, for the purpose of revision, if you have watched our video on reaction of alkenes, oxidation of alkenes with hot concentrated acidified manganate 7 ion, and with cold dilute acidified manganate 7 ion, you will see this. You can go back again and watch the video. Now, when the acidified manganate 7 is hot and concentrated, propanoic acid is the only organic product. Listen once more. When acidified manganate 7 is hot and concentrated, propanoic acid is the only organic product. When acidified manganate 7 is cold and dilute, the organic product is T, which has two chiral centers. Give the structural formula of V and T. Once more for the purpose of revision. If you can go back to our reaction of alkenes, oxidation of alkene with under hot concentrated manganate acidified manganate 7, you will see that under this harsh condition, the double bond in alkene is broken. The double bond in alkane is broken. And when the double bond in alkane is broken, the product form will depend. The product form will depend on the position of the double bond. For instance, in a place where if the end of the double bond has two hydrogen atoms there, the end product will be carbon dioxide and water. If the end of the molecule, if the end of the double bond, if the molecule at the end of the double bond has two alkyl groups, if it has two alkyl groups there, and when the bond breaks, that portion of the molecule will produce but ketones. But that is not the case here. Lastly, if the end of the double bond has a hydrogen atom and an alkyl group, one hydrogen atom and an alkyl group there, it will result in what? It will result in an aldehyde. And remember, aldehydes undergo oxidation to what? To carboxylic acid. So, if the examiner is telling us that under this condition, propanoic acid is the only organic product, therefore, we can conclude that that end of the alkene molecule, that end of V, the V is an alkene. So that end of the molecule that produces this, after the breaking of the double bond, that end of the molecule will contain what? It will definitely contain an aldehyde. And this is how it is represented. Let's do this as an example. We have this. We have this as an alkane, propanoic acid. We have this as this alkane. We have this an aldehyde. Oh, sorry. We have this, let me say, carbon. We have this. And under this harsh condition, it undergoes oxidation with the hot concentrated. It will be 2, yeah. Under this harsh condition, what we are going to have here will be this compound. And when there is, under this harsh condition, the double bond breaks. And this will be the molecule that will be formed. This will be the molecule that will be formed. We will have this and this, plus we will also have and remember all these are all aldehyde, and they will undergo further oxidation to what we call to this compound, carboxylic acid. So this is the same thing we are having there. If we have got 2 molecules of aldehyde will be formed. So if we have got this, if this is the same way, and we have propanoic acid, so this is how the whole thing is supposed to look like. And this is how we are supposed to have our molecule for propanoic acid. In propanoic acid, this is what we are supposed to have. Our molecule is like this. Why? If it undergoes oxidation, what will happen there? There will be a splitting here under the harsh condition, hot and concentrated acidified manganate 7. It will split there, and the result will be this one. The result will be H. One of the oxygen here will attach itself here, and this will be the carbon, and this will be the hydrogen. Plus this other one here, which will be this. Remember, these are aldehydes. 1, 2, 3, propanol. All these will undergo further oxidation. They will undergo further oxidation to do to what? They will undergo further oxidation to corresponding carboxylic acid, to corresponding propanoic acid. That will be CH3, H3, C, CH2, C. The same, there are 2 molecules of this. So 2 molecules of this will be produced from here. That is why the examiner says, so when the bond splits, it gives us 2 molecules of the aldehyde that will be formed. Aldehyde are further oxidized to what? To carboxylic acid. Now, our question now is, give the structural formula of V and the T. And V is what? Our V, structural formula for our V, the structural formula for our V will definitely be what? Will be from here. This is our structural formula for V. CH3, CH2, CH double bond, CH double bond, CH, CH2, and CH3. That is supposed to be our formula for V. Structural formula for V. So our structural formula for V will be CH3, CH2, that we said there, CH2, CH, a double bond, CH, CH2, and the CH3. Then T, under cold dilute, under cold dilute. Remember that under cold dilute, if you can go back to our previous video on this, under cold dilute, a diol is formed. Under cold dilute, a diol is formed. So under this cold diol, under this, a diol is formed. So we are saying that under this condition, a diol is formed. So under this condition, see what will be formed here. A diol is formed here. Under this condition, this is what is happening. Under cold dilute, this is the reaction that occurs under cold dilute. Under cold dilute, it will be oxidation. There will be oxidation plus water. Cold dilute. Oxidation, then that is oxidation taking place, and since it is dilute, water is needed. And that will result in a diol. And this is the product that is formed. This will be the product. We will have H, 3C, CH2, CH2, C. Let me put this one up here. Here, the oxygen now comes here is from here. I mean the OH comes here. The diol is from within the two double bonds. Go back again. We will have this. The diol is from here. We'll have CH2 and the CH3. Under this condition, you will see here that this carbon is a chiral carbon. This carbon is also a chiral carbon. Why do I say so? On this carbon, we have a hydrogen group. We have an alkyl group here, which is an ethyl group. We have an OH group here, and entirely we have this other group here. So there are four different groups. This group, this other one, and this other one, and entirely this other one. On the other side again, this carbon again, we have this OH group, we have this ethyl group, we have this, and again, this other side is another group. So these are two chiral carbon atoms are resulting from this. So now let's go to our question paper and answer our question. The structural formula for T would be For T, I will give you the structural formula for T will be T will be CH CH3 CH2 CH OH OH CH OH CHOH CH2 and CH3. That will be the structural formula for T. Identify the types of isomerism shown by V and T. Okay, initially this is V. Initially this is V. Initially this is V, as you are seeing, this is V. And this is T. Okay, which organic molecule? There are two types of isomerism. We will have structural and geometric, structural and stereoisomerism. Stereoisomerism, they are in two types. We have geometric and we have optical. Here, a geometric isomerism will only occur in compounds with double bonds. When there's because of the non-rotation of the carbon-carbon double bond, geometric isomerism will occur here. Therefore, we will say V will undergo geometric isomerism, or what we call cis and trans isomerism. Then this is T. T is the other type of isomerism, optical isomerism. And the condition for optical isomerism is a compound where a molecule that has it must have a carbon atom with four different groups. Here in optical isomers, there is a carbon atom here. There's a chiral carbon. There's a chiral carbon here, and there's also a chiral carbon here. So in that case, T will undergo optical isomerism, while V will undergo geometric isomerism, or what we call cis-trans isomerism. Go to your question paper and you do it there like that. We say V will undergo geometric isomerism. Geometric or cis-trans cis-trans isomerism. Then T will undergo what? Optical isomerism. If you do that, you are fine. It takes us to the last section of our question. Another question which is has to do with alcohols. X is CH3, CHOH, CH2, CH3. The reaction between X and alkaline aqueous iodine produces a yellow precipitate. Give the name of the compound formed as a yellow precipitate in this reaction. Remember, alcohols, only secondary alcohol will undergo this reaction to produce a yellow precipitate. And those yellow precipitate are what we call the triiodomethane. It will undergo a triiodomethane reaction. And the name of that yellow precipitate will be a triiodomethane. Triiodomethane. A triiodomethane, or what we call the iodoform. And it is usually like this. It is a CHI3. Because of time, I would have loved to show how the reaction goes to give this, but go back to our previous video and you'll get it there. Give the name of X. The name of X of this compound, we have the first carbon, the second carbon, third and fourth, and the OH group is located on the second carbon. In that case, there are 4 carbon atoms, so it's supposed to be butanol, but the OH group is located on the second carbon. We now say it is butan2-ol. It's a butan2-ol. Now we now go. It takes us to the B part of it. It takes us to the B part of it. The B part of it gives says there are 3 structural isomers of X, and there are and that are alcohols. Draw the structures of these 3 isomers of X. The structures. So now, this the first isomer. The first structure is this one. The first structure, of course, it will give us different structures: primary alcohol, secondary alcohol, and tertiary alcohol. Let's see how it can give us the primary alcohol. It will be 1, 2, 3, 4. One, two, three, four. That is a primary alcohol. This is a primary alcohol. Now, it will give us a secondary alcohol. In that case, the secondary alcohol is it will have 1, 2, 3. Okay. And 4. Here we have, I can just say CH3. I can say OH. Yeah. I can say, let me say CH2. I can say this is CH3. Well, if you draw this structure, it is acceptable. That is a secondary alcohol. Now, a tertiary alcohol in this case, will contain, let me say a CH3. Let me say CH3. It will be like this one. Yeah. You have this, you have that. That is a tertiary alcohol. So this, if you draw these structures, you will have your 2 marks. Now, 2 reactions of X are shown. This one, reaction 1, gives what? A ketone. And reaction 2 will give what? It gives an alkene. Now, this is oxidation to a ketone, and this is, I said there's dehydration here to give an alkene. Identify the type of reaction involved in 1. Of course, primary alcohol are oxidized to carboxylic acid. Secondary alcohol are oxidized to ketone. So in this case, 1 is oxidation reaction. Oxidation reaction. Identify the reagent for 1. There are 2 reagents: acidified potassium dichromate 6 solution, or acidified potassium manganate 7 solution. You can write it like this. You can use the formula by writing it. You can say, identify the reagent. You can say acidified You can say this, you can use this one. You can do this or this one. Or you can write in words. No problem. If the space is there. And number 3, reaction 2 can be carried out by passing the vapor over hot aluminum oxide. The product the product of reaction 2, which is a butene, is actually a mixture of 3 isomers. Give the full names of the 3 isomers formed by 2. You will realize that for the purpose of revision, excuse me, for the purpose of revision, you will have a butane will have C4 C4H8. In that case, we can have C, we can have a double bond, a compound like this. We can have a compound like this one. And in that case, this is a trans isomer. This other one, we can have another structure like this. In that case, we have CH3 and CH3. We'll have a cis isomer, and in this other case, we can have a structure like this. Something like this. We can have a structure like this. We have cis. The first one, if I were to name the first one, I would say it is, this one is trans isomer, trans butene. I would say it is trans butene. The second one, I will say it is cis butene. And this one is but1-ene. But1-ene. So these are the names based on this structure I have given here. You can have. It takes us to the D part. The D part of this reaction, say the reaction of methylpropene with methylpropene with hydrogen bromide produces a mixture of 2 halogenoalkanes. One of the halogenoalkane, which is 2-bromo-2-methylpropane, is formed as the major product, while 1-bromo-2-methylpropane is formed in small quantities. Complete the mechanism to show the reaction of methylpropene with hydrogen bromide to form major products. Include the structures of the intermediate and all necessary charges, the dipoles, lone pairs, and curly arrows. The structure of 2-bromo-2-methylpropane is not required. So now, reaction of alkene. This is a reaction of hydrogen bromide with an unsymmetrical alkene. This is an unsymmetrical alkene. And in this case, this is what you are going to find. The first thing is, in this structure, the first thing you are supposed to do here is to show the polarity of the hydrogen bromide. So this one is has because of electronegativity, partial negative. Let me do it this way. Okay. I say this is negative, positive. So in this case, what happens here? What happens here is this is a double bond, high density of a cloud of electrons here. But what is going to happen here is the pi electrons. They are the pi electrons that are reacting here. The hydrogen here is going to act as an electrophile, and electrophiles are electron pair acceptors. Then there's going to be what we call heterolytic fission between hydrogen and the bromine. Now, you should know that as the pi electrons come closer to the hydrogen bromide bond, what happens? There is repulsion. There is repulsion. There is repulsion in this bond. Electrons, the bonding electrons here are repelled towards the bromine. Let me just show you what is happening. As the pi electrons here are approaching it, this is what is happening. Okay, what happens? As the pi electron are approaching this bond here, as they are approaching it, the bonding electrons here are pushed towards bromine. And finally it results in a heterolytic fission. It results in a heterolytic fission. So when that happens, there is a complex that is being formed here, an intermediate. The intermediate form here will be there will be H3 carbon this is the hydrogen that will attach itself here. That will be the hydrogen. And what happens? There is a carbocation here that is being formed. A carbocation there is formed. There is a carbocation there. And this carbocation, this is a carbocation here that is being formed. And that is what is happening there. Explain why 2-bromo-2 methylpropane is the major product. Now, at this stage, I told you, as the electrons are approaching here, as the pi electrons are approaching this HBr bond, the bonding electrons here are repelled towards bromine. Eventually, it leads to what? Heterolytic fission with bromine going as a bromide ion with a lone pair of electrons. So this is the bromine here. This is the bromine with the lone pair of electron here. This is the lone pair of electron. And it's a bromide ion. It's a bromide ion. But subsequently, it doesn't end there because there's going to be an attack again. This carbocation is highly reactive. For that reason, it is attracted to the lone pair of electron here. Let me use another this thing to show what is going on here. You know, here we'll have this attacking this one here. You see now, it now attacks that one there. And that will finally result in what we will say it is 2-bromo, 2-methyl propane. For revision purpose, please, I want you to better understand this. For revision purpose, addition of HBr to an unsymmetrical alkene. Remember, when an unsymmetrical alkene is added to an HBr, there are two ways a reaction can occur. The hydrogen, after the heterolytic fission, the hydrogen could do what? Could attach itself to this carbon atom here. It could attach itself here or here. If it attaches itself here, A is our product. If it attaches itself here, B is our product. Okay. If it attaches itself here, this will be our product. You see what is happening? Okay. It is formed from what? From a tertiary carbocation. Now, on the other hand, if hydrogen decides to attach itself, but here B is formed, and what happened? This is a primary carbocation that is being formed. This is a primary carbocation. There is only one alkyl group attached to the partial positive carbon. This is a primary carbocation. There is, in this case, it is a tertiary carbocation. In this other case, it is a primary carbocation. And in that case, as we said, because of the electron inductive effect of the carbocation, in other words, alkyl groups are electron donating. When they donate electron on this partial positive, on this positively charged carbon, they help to reduce the negative charges on it. They help to reduce, they help to reduce the charge density on the positively charged carbon, and making the carbon to be what? To be energetically more stable. But in this case, there's only one alkyl group that is donating here. There's only one alkyl group that is donating here. Here there are 2-3 alkyl groups donating. This one donating, and this one donating. This reduces the charge density on the positively charged carbon, and making this carbon to be energetically more stable than this one, where donation is coming from only one end. In this case, this carbon atom is relatively unstable, and this result in what? It also result in a high activation energy. For that purpose, any product that is formed from this carbocation, which is energetically stable, is the major product. Any one from here is not a major product because it is really unstable. And we are told 2-bromo, 2-methyl propane is our main product and is the major product. It is highly stable because of the inductive effect of the methyl groups. This one is less stable, and it is the least stable product. So it takes us to our reaction, to our question. Explain why 2-bromo, 2-methyl propane is the major product of this reaction. We can say because 2-bromo, 2-methyl propane is the major product because it results from a tertiary carbocation. I can say it results from a result from a tertiary carbo a result from a tertiary carbocation, which is relatively more stable than the primary carbocation. Due to what? Due to the electron donating effect. Due to the electron donating effect, or we can say the positive inductive effect. Positive inductive effect. Positive inductive effect of the what? Of the three methyl groups on the positively charged carbon. So that is it. This product, from what I just explained for you for the purpose of revision, has resulted from a tertiary carbocation, which is relatively more stable than the primary carbocation due to the electron donating effect. This is as a result of the electron donating effect or the positive inductive effect of the three methyl groups on the positively charged carbon. As I said, the positively charged the methyl groups. As I said, the methyl group in this case here, there are three methyl groups here. The three methyl groups here are electron donating. As they donate more electrons, because there are many of them, 1, 2, 3, they help to reduce the charge density on the positively charged carbon and make this molecule what? Energetically more stable. But this one is less stable. There's only one alkyl group here that is donating. It does not reduce the charge density here. It has just little effect on this positively charged carbon. Therefore, this molecule is relatively unstable. And this results in a very high activation energy for this carbocation. In that case, a product from here is more stable and a major product than a product that is from this one. And that is why we say this one is the major product. Learners, go back to the videos, our previous video, and you will learn more from there. This is all we can provide for you now. Continue to watch our video. You will have many more of these questions before your exam come up. Thank you for watching. Remember, if you haven't subscribed to our channel, please subscribe and hit the notification bell. Thank you very much once more.